Welcome back, everyone. We continue in our functions unit. We're currently on lesson 5, and this topic is a little bit different than what we've been doing. It's called composition of functions. And really, in essence, it's combining two functions, not with adding or subtracting, multiplying or dividing, but more one function going inside of another function. And we're going to take a look at a couple real life examples for that on this first page. So when a pebble is dropped in a pool of water, ripples in the shape of circles form on the surface of the water. The radius of the outer ripple is given by the formula r equals 0.3t. We're going to need that later, where r is the radius in meters and t is the time in seconds after the pebble hits the water. If the area of the circle is a equals pi r squared, combine this formula with the radius formula for the outer ripple to write a formula for the area of the circular ripple after t seconds. Okay, the very last part there is kind of the key to how to set this up. They're asking for a formula for the area of the ripple after t seconds. So they're implying that we need to have area on one side of the equation, equal sign, and t on the other side. But right now we only have a equals pi r squared. Okay, that's not in terms of time, but in terms of r, the radius. But we do know up here r is equivalent to 0.3t. So we could take this, which is what r is equal to, and sub it in for r here. So let's do that. Area equals pi, replacing r with 0.3t. And then, of course, we could simplify that further, but we're going to stop there. We have now a in terms of t, a formula where if we knew t, we could actually figure out the area of the circle. Okay, let's look at another example of one of those. Okay, a 3.5 liter V6 2012 Toyota Camry has a fuel efficiency of approximately 8.2 liters per 100 kilometers. The cost of gasoline is 1.25 per liter. Okay, so this time they're not handing us the equations like they did in the last one. So we're probably going to have to, yes we are, we're going to have to come up with them. The volume L in liters of fuel used can be written as a function of the distance d kilometers traveled. Complete the following for L in terms of d. Okay, well, kind of off to the side, I'm going to write this down. They told us that it was 8.2 liters per 100 kilometers. Okay, now if we want L to be in liters, we can use this as long as we multiply by kilometers, and the kilometers units will cancel. Well, D is in kilometers, so if we go D kilometers, kilometers will cancel or divide, and we'll be left with this. So now we're going to drop this liters here, but in essence now we can see our units are in liters, which is what we wanted. So just taking the numbers and our variable d, our equation would be 8.2 divided by 100 d. Okay, let's try the next one. The cost C in dollars, so we want to end up with a unit of dollars, of gasoline used can be written as a function of L. Okay, complete the following for C in terms of L. Okay, so what did they tell us about the cost? They said it's 1.25, $1.25 per liter, per 1 liter if you like. Okay, if we want dollars, C has to be in dollars, we need to get rid of that unit of liters again. So we need to multiply by liters, and look at that, L is actually in terms of liters, so we'll write the variable L, and that's liters, which would get rid of the liters for us. And then we don't need to write that $1.25 over top of 1, because divided by 1 it's still $1.25, and then our variable L. There we go, C in terms of L. C and then the variable of L on this side. Okay, finally, we can find the cost of the gasoline in terms of the distance traveled by combining these two functions. Okay, so we want cost in terms of distance, so we need to have D on the right-hand side and C on the left-hand side. If we substitute the formula for the first function into the formula for the second function, we can write C as a function of D. Okay, so our second function was 1.25 L. But we know from up here that L is equivalent to that. So we're going to scoop L out and put 8.2 over 100 D in. And then we'll just write that this is C. Move that C over a little bit. There we go. We have C as a function of, or in terms of, D. C is a function of D. And there we go. So when two functions are combined in this manner, we say the new function is a composition of the other two functions. And that's what we're doing here. Okay, we are probably going to skip this investigation. Okay, we're going to look at the format of how this is written. Okay, the composite function h of x can be written in the form, so this is important, h of x equals g of f of x. Okay, and it's said like this. You'll notice I'm saying of, right? Or this funky little open dot is another way to write it. So g of f of x. Okay. So, and what that means is you're subbing the function f of x in for x in g of x. Sounds more confusing when you say that, right? Okay, we're going to go to the next page and look at that. Okay, so on this next page, they're outlining basically the steps in how you would do a question. And I think probably what I'll just do is jump into this first example, and which are basically following these steps, and you'll see how it goes. Okay, so given f of x equals 10x plus 1 and g of x equals 2x minus 5, complete the work below to determine g of f of x. So first of all, when you see the composition function given to you like that, first thing you want to do is rewrite it like this. So g bracket f bracket x bracket. Because then you can see what you're actually going to be doing. You're going to be replacing f of x. So up here, this is what f of x was equal to. So we are going to replace that in the function. So now it's g at, or g of, 10x plus 1. All right, now we know g of x, just off to the side here, is equal to 2x minus 5. So if we want to be replacing x with all of this, 10x plus 1, guess what? In here then, we're scooping x out and we're putting in 10x plus 1. So what we would do is basically go, oh, so we don't need to write g anymore because we're actually going to use the function g. So we'd have 2 brackets minus 5. Everywhere we saw x, in goes the new x, which is 10x plus 1. Okay, now we want to simplify. So we'd multiply the 2 through to get 20x plus 2 minus 5, and then finally we collect like terms and we'd have 20x minus 3. Okay, so that's the general idea with these ones. Let's look at example 4. We have if f of x equals 2x squared minus 1 and g of x equals 3x minus 4, find g of f of x. So first step, g bracket f bracket of x, like that. Replace f of x with what it equals. So that's going to go in here. And now this becomes g at 2x squared minus 1. Which means instead of x in g of x, we are writing 2x squared minus 1. So this would become, so we're replacing it here, 3 scooping x out, minus 4, there's our g of x function, and we're replacing x with 2x squared minus 1. See how the f function went inside the g function for x? We're replacing it. Okay, just need to simplify this now. 6x squared minus 3 minus 4. Oh, missed the squared. There we go. 6x squared minus 7. And that should be our simplified final answer. All right, now this one looks a little weird. Looks like GOG, I suppose, but let's rewrite it how in the other notation. So g of x. So it's a little weird when you try and get your mind around this, but we are replacing x in g of x with the function g of x. I know, crazy, right? Okay, so let's first of all replace g of x with what it equals, which is 3x minus 4. That goes in, replacing g of x here. Okay, now our g of x function is 3x minus 4, so we're going to now replace x with our new x. So scooping that out, 3, leave room for our new x minus 4, and our new x is 3x minus 4. All right, so now we just simplify that, multiply the 3 through, and we would end up with 9x minus 16. And there we go, simplified final answer. All right, so we're going to look at the next page. Okay, so on this page we're going to look at the domain and range of a composite function because there's some weird things that happen when we do this. So we're starting with the functions f of x equals x squared minus 3 and g of x equals the root of x minus 1. Now, they want us, first of all, without finding a formula for f of g of x or g of f of x, they want us to evaluate. So basically what they're saying, and I am going to, we're not really finding a formula, but I am going to write this a little differently. Okay, that other notation, it's easier to look at. What we're going to do is we're going to concentrate on finding the inside there, which is g at 2. So we know g of x is equal to the root of x minus 1. And if we want to know what g at 2 is, then we're going to replace x with 2. Don't know why we're getting a beeping. Okay. And then if you simplify that, we get 2 minus 1. The root of 1 is 1. Okay, so now we have g at 2. So what we're going to do is go back to this and we're going to replace g at 2 with 1. And now we need to find f at 1. Well, if you look at our f of x function up here, what we're going to do is scoop out x in x squared minus 3 and replace it with a 1. Simplifying that, 1 squared minus 3 is going to equal negative 2. And there we go. That would be our answer. And we didn't actually find the formula that still had x in it. We just used numbers. Okay. Next example, f at g at 0. So let's again write it in this form. Okay, and we want to focus on finding g at 0 first. So I know g at x. They don't give you a lot of room here, do they? G of x equals the root of x minus 1. I am putting 0 in for x. And I'm going to be calculating the square root of 0 minus 1. Now, if you try that on your calculator, you're going to get a big error, okay? Because you'd be trying to square root negative 1. Well, if we're staying in the real number systems, you can't do that. So as a result, this is undefined, or it doesn't exist, right? Not a real number. Okay, so as a result, it is impossible to get f at g at 0. Okay, let's try the next two. Actually, you guys go ahead and work on the next two, and then we'll see if we get the same answer. So pause your video and work on these two, this one, and then we'll check back. Okay, so for the third one, g at f at 2, we go off and we find f at 2 to be equal to 1. We sub back in so that now we're determining g at 1. So we sub 1 in for x and g of x, and we get the square root of 0, which is 0. So that one's all good. Next one, we have g at f at 0, so we rewrite that. Focus on the inner part, f at 0, sub 0 in, we get negative 3. Come back, replace f at 0 with negative 3, and we have g at negative 3. So now replacing x in our function g of x with negative 3, we end up with the square root of negative 4. Again, not a real number to do that. So as a result, we can say that g at f at 0 does not exist. Okay, part B. State the domains of f and g. Okay, so when we're looking at domain, we could probably figure that out from the equations. Range, however, is sometimes a little bit easier if we use a graphing calculator for that. So why don't we just jump to that and we'll graph this in y1, and then we'll graph g of x in y2, and take a look at the domain and range from those graphs. Okay, so grab your graphing calculator.